Prenatal Genetics, Part 1, Non-Invasive Screening, Module 3, Lecture 4 in the Genetics series. Prenatal screening is screening that was developed to detect common birth defects in the fetus before birth. These disorders or defects often occur during pregnancies that aren't known to be at increased risk. Screening is usually non-invasive or low risk, including maternal blood sampling as well as ultrasound. There are a number of complications that can occur during embryonic development. Some developmental anomalies result from inherited genes or chromosomal aneuploidies. Others can result from teratogenic effects. In aneuploidy screening, prenatal screening is used to detect fetal aneuploidy. There is an increasing risk for aneuploidy with increasing maternal age. This is due to non-disjunction. Women are actually born with all the eggs that they have before birth. They start the meiotic process, and then they're held in kind of a suspended animation. There are a number of things that can happen to this woman: radiation, infections, other things that can increase the risk of problems occurring with that non-disjunction. Advanced maternal age is defined as over the age of 35 at the time of delivery. However, a woman can have a baby with a chromosomal aneuploidy or any other anomaly at any age. Here is the prevalence of deliveries with babies with problems as a woman gets older. And here is a table, and this data was attained in the 1970s. At the age of 20 in the first trimester, the risk to have a baby with Down syndrome is about 1 in 846. By the second trimester, it's 1 in 1142. And by the third trimester, it's 1 in 1482. The reason this decreases is only approximately 60% of babies conceived with Down syndrome make it to term. The risk for any chromosomal problem is about 1 in 526. By the age of 30, your risk now increases in the first trimester of having a baby with Down syndrome to 1 in 567, 1 in 765 in the second, by the third, and any chromosomal abnormality 1 in 385. At age 35, now you're up to 1 in 230 in the first trimester, and 1 in 403 in the third trimester, with the risk of having a baby, or any baby with any chromosome problem, of 1 in 179. But what makes it, now when you actually get to, your late 30s to your 40s, the risk of having a baby with some type of chromosomal abnormality really increases. But why is it that when you're 34 and the risk of a baby with a chromosomal abnormality at delivery is 1 in 244, and at 35, 1 in 179, that doesn't seem like a big number. The reason amnio was recommended at the age of 35 is that the original studies done in the 1970s for amniocentesis, which we're going to describe in the next lecture, the risk of pregnancy loss was estimated at 1 in 200. And so they said to themselves, why would you offer a procedure that's more likely to result in loss of the pregnancy than an abnormal result? And that's how the age of 35 magically occurred. It has little to do with science. Today, under ultrasound guidance, the risk of pregnancy loss due to amnio is like 1 in 500. So in this case, pretty much everybody should be offered an amnio, and yet fewer and fewer women want that because they don't want to take the risk of 1 in 200, 1 in 500, or 1 in 1,000. Ultrasound is a non-invasive method to look at the baby. And here's a 2D, and here we have even a 3D ultrasound in the womb. Between 11 and 13 weeks, we can actually look at a number of markers of the fetus and make those determinations as far as the risk of having a chromosomal aneuploidy. One of the most important is nuchal translucency, the absence of the nasal bone, as well as some heart markers such as ductus venosus and tricuspid regurg. Here we have an enlarged nuclear translucency, and you can get with 95% adjustment for the risk of Down syndrome, trisomy 18, 13. Look for some heart defects as well as some other genetic syndromes. The other thing is a maternal serum screening. Maternal serum screening has been around for about 20 years, different variations of which. And basically, the blood of the mother is drawn between 16 and 20 weeks. There are, in a triple screen, there are quad screen, there are 4 components looked at. Alpha-fetoprotein, HCG, estriol inhibitor. Alpha-fetoprotein is the only one that's indicative of a neural tube defect, and it's actually the most specific. So when alpha-fetoprotein is significantly elevated, it's a sign that there's a neural tube defect in the fetus. With Down syndrome, the AFP and the estriol are low with HCG and inhibin A elevated. And with everything low, there's a risk for trisomy 18. And so a number will be given for the risk, and in ultrasound and invasive testing such as amnio is then recommended as follow-up. So, when the AFP is elevated, it may indicate a neural tube defect such as spina bifida, or even an abdominal wall defect such as gastroschisis or omphalocele. When the AFP is low and the beta HCG is high, it may indicate Down syndrome. So, a positive screen for a quad screen is greater than 1 in 270. So the next step is diagnostic testing. So of those 270 women that are tested, 1 will have a baby with Downs, and the other 269 will not. A very, very positive screen is 1 in 10. That's a very positive screen for Down syndrome. However, there's only a 10% chance that the baby actually has Down syndrome. Level 2 ultrasound is usually done around 20 weeks gestation, and there's a 50 to 60% detection rate for Down syndrome. It looks for signs of the heart, short femurs and humerus, obstruction in the intestines known as duodenal atresia that can cause something called a double bubble sign, as well as the enlarged or thick nuchal fold. There's also a 90+ detection rate for trisomy 13 to 18. Trisomy 18 includes a strawberry-shaped head, heart defects, and brain malformations, a clenched hand and recto-bottom feet. Signs of trisomy 13 include facial clefts, brain malformations, including holoprosencephaly, heart defects, additional digits such as polydactyly and recto-bottom feet. There's also a 90% detection rate for neural tube defects. But one of the newer techniques that's very accurate is cell-free DNA. DNA originating from the placenta makes its way to the maternal circulation. And we've recently been able to isolate enough of this DNA in the maternal circulation to do analysis. 10% of the cell-free DNA in a pregnant woman is fetal DNA. The total amount of circulating placental DNA increases with gestational age. These screening tests are available starting around 10 weeks. So again, the cell-free DNA or free fetal DNA is placental DNA that makes its way into the maternal circulation. So circulating fetal DNA fragments do account for significantly less of the total DNA in the maternal serum. Fetal DNA arises from apoptosis trophoblast cells, and the total amount of free fetal DNA increases with gestational age. Now here's a diagram of chromosome 1 and chromosome 21. The orange is the maternal component of chromosome 1, and the green is the fetal. And because 21 is much smaller, there's less fragments of both of the maternal and fetal. So what we do is compare these chromosomes to each other. When there are additional fragments than what would be expected, we are assuming that these additional fragments are of fetal origin. And that's true most of the time, except for what if the mother had triple X and she had a male fetus? You might think that the fetus had Klinefelter syndrome. One of the methods it's used is a counting method. So we compare the DNA on chromosome 1 to 13, chromosome 2 to 18, and chromosome 3 to 21. So, in the counting method, here are our fragments from chromosome 21, and here are fragments from chromosome 3. Again, chromosome 3 is a much larger chromosome, so we'd expect 20% of the fragments to be of chromosome 21 origin, with 80% in chromosome 3. However, what if we have additional fragments of chromosome 21 origin? This changes the observed amount, and this brings up the concern that there is additional copy of chromosome 21 in the fetus. High-risk population is defined, whether rightly or wrongly, as women over the age of 35. A positive cell-free DNA for trisomy 21 is associated with a greater than 99% chance that the baby has Down syndrome. The true positive for trisomy 18 is 97%, and cell-free DNA can also look at trisomy 13, which quad screens cannot, and there's about an 80% detection rate. The reason it's probably lower in trisomy 13 is because the placenta is not particularly healthy in a trisomy 13 fetus, and often the fetal fraction is low. In the low-risk population, recently a study was done in New England Journal of Medicine, and they looked at 15,841 low-risk women, and they did both the quad screen and cell-free DNA. In the cell-free DNA, 47 high-risk were found to be high-risk for Down syndrome. 9 did not have it. So they actually did have positive, risk for Down syndrome, but did not have it. However, of the 15,794 women that had low risk, none had a baby with Down syndrome. So the positive predictive value for this test, unlike in the high-risk population where it's 99%, is 80.9% or 81%. In comparison to the quad screen, of 800, instead of 47 women being positive, we had 884, of which 30 actually had a baby with Down syndrome. Of the 14,949 negative results, 8 actually did have a Down syndrome baby. So the positive predictive value of the quad screen is 3.4%. So you can see that the cell-free DNA far exceeds the quad screen with regards to this, in addition to the fact that instead of having to call 47 women and only having 9 that actually didn't, or 8 that didn't have a baby with Down, 9 that didn't have a baby with Down syndrome, you have to call 884 women back to find, and the majority, only 30 of these women actually had a baby with Down syndrome. So, as I stated, cell-free DNA originates from placental DNA. At conception, the egg and sperm fuse and divide 4 times. At the 16-cell stage, 13 cells become the placenta and 3 cells become the baby. If the pregnancy starts as aneuploidy, but in one of these early cell stages, the additional copy is lost, then the baby can actually have normal chromosomes, but the placenta has aneuploidy. And this probably is the vast majority of cases of false positive. Placenta nourishes the fetus, so even when there is a false positive, if there's aneuploidy in the placenta, this can result in intrauterine growth retardation in the fetus. And here's just an example of mosaicism. Sometimes it's in the fetus and the embryo. Sometimes it's just in the placenta. Sometimes it's just in the baby. So, Which of the following is a benefit of prenatal screening for chromosomal aneuploidies? Can screen all chromosomal abnormalities, guide decisions for further testing, more accurate than CVS and amnio, provide a diagnosis without invasive procedures, or can only be used for Down syndrome. This concludes the Module 3, Lecture 6 in the genetic section.